All right, let's look at this one next. By the way, number 6 and 7 on that sheet from today are also of the same form as the previous question, so that you should be able to use tabular method on both of those things. 4 and 5 require a bit of spice, and that's why above this block of questions I said, before you start doing these problems, think about whether this is a very mild problem with no seasoning, or is it going to be something that makes you hurt later. So 4 and 5 are actually both examples of things that require you to think outside the box. And in fact, those are the only two problems where U substitution might actually be a good idea. In fact, you can't really get out of these questions unless you do use substitution. But again, I want you to take to heart this idea of this is a hard question. I don't want to solve it. I don't know how to solve it. So I'm going to change it to something else that maybe I do know how to solve. So I'll sketch this out and I'll sketch out the other one and then we'll see where it goes. So let's try just, it's a product. Actually, no, not a product. It's a composition. So it's not even a product. So the stuff for products doesn't make sense. It's not a quotient, so the stuff for quotients doesn't make sense, which means we may need to do a change of variable or use substitution to either create a product or create a quotient and then continue solving the problem. So questions where you just have a single function. So this is just sine of ln of x. There's no plus, there's no minus, there's no product, there's no multiplication, there's no quotient. Here, 9 times out of 10, either you just have to know it, meaning the integral of sine x is negative cosine x, or you have to use U substitution to make it into a product or make it into a quotient so that you can then use some other technique. So here, let's say we let U equal to ln of x. Then du dx, we take the derivative of both sides with respect to x. That'll give us 1 over x. And du will then be 1 over x dx. So we can say, okay, we are in x land here. We can try to convert everything to u. The problem is, if I start to move this to u land, I can rewrite this problem as sine of ln of x turns into u. And now I have a dx here. But in order to rewrite this problem as a du, I have a 1 over x dx. I don't have just the dx. So one thing that you can say is, I need to get rid of just the dx by itself. Or you can rewrite this as x du equals dx. Because I can replace this with sine of u, but then the dx I'm getting stuck with. And usually these are the problems where you use that as a hint and say, I don't have this extra x or 1 over x anywhere in my original problem. When that happens, 99% of the time means you have to go back here and solve for x. So these are sort of hallmarks of these questions where you just have a single function, maybe a composition, but it's still just one function, not a product or a quotient or a sum or a difference. You just have one single thing. You try to do a change of variable and convert it into a U substitution maybe, or turn it into a product or a quotient. And as you're doing U substitution, you're always going to be left over with either a 1 over x or an x or something like this. It might be a 3x, it might be a 5x squared, but you're going to be left with some function of x that is not present here in the original problem. Every single time, 99% of the times, you have to go back to your original substitution and solve for x. And because that's the scenario here, if u is equal to ln of x, we can rewrite this logarithmic equation in its exponential form. You should have done this in college algebra ad nauseum. So you rewrite this as e to the u equals e to the ln of x. You raise both sides to powers of e. That's how you convert logarithmic equations to exponential equations. And because these are inverses of each other, that goes away. And you can say e to the u is equal to x. So that means when I make the substitution, thus, when I say that x du is equal to dx, this implies that e to the u du is also equal to dx because we just proved that right here. If e to the u is the same as x, I can replace this x with e to the u. So now I'm okay with going to u land because I can replace this dx with this guy, e to the u du. And notice that we now have a product of two functions. So here I'm going to let you take over. I'll pause the video and let you continue with this problem. One of these two functions has to be u, or not u, choose different letters, r and s if you like. You don't want to reuse a variable that's already in the problem. And the way you choose r or s is, again, using laity. So we don't have any logs, we don't have any inverse trigs, we don't have any algebraics, but we do have a trig function. So let r, I'll start you off, but I'm going to have you finish. Let r equal sine of u, and we're going to therefore let ds equal e to the u du. So this portion will become r, this portion will become ds. So this would imply s would equal e to the u, and oops, dr would be cosine of u. Apply parts, and you should have your answer pretty painlessly. I'll give you a hint for the next one, or the previous one, which was number 4. So this one was the integral of t cubed times e to the t squared dt. So here again, we have a product, so we should try to undo it by chain rule first. The derivative of t cubed is 3t squared. Problem is I don't just have a t squared. I have an e raised to the t squared. So that's unfortunately not going to work. And here, if I take e to the t squared and I find the derivative of it, I'm going to get another e to the t squared times 2t. And there's no way for me to convert t cubed into that. Then I can say, okay, parts. Can I do tabular method on this? The tabular method means I have to have x to the n or t to the n. So let's actually just briefly entertain it. This is my derivative column, so I have t cubed, 3t squared, 6t, 6, and then 0. So far, so good. So the derivatives are easy to find. The problem is with the integrals. E to the t squared. What's the antiderivative of that? In fact, it's incredibly difficult to find the antiderivative or the integral of e to the t squared, which is why this is not a candidate for the tabular method. Again, I know I'm beating a dead horse here. It has to be x to the n times sine of something linear. So ax, never ax squared, or x to the n times cosine of ax, something linear again, or x to the n times e raised to the ax, something linear again. Here we have a quadratic function. Cannot use tabular method on this. So the shortcut's not going to work. So then we say, okay, well, let's just try regular integration by parts. Let's consider what we should pick for laity. So that means I have an algebraic function, so that's going to be u. Okay, I'm using shorthand here just to prove a point. This is not how you should write your solutions. So if u is equal to t cubed, then du will be 3t squared dt. That's okay, I can find the derivative. But then dv is going to be e to the t squared, and here I need to find the antiderivative, or the integral, in order to find v. But I run into the same problem I ran with, what's it called? With the tabular method, because I cannot integrate this guy. It's not simple. In fact, it's an incredibly difficult problem. to integrate e to the x squared or e to the t squared. So we're kind of stuck here. I've tried undoing chain rule. I've tried undoing or just undoing the product rule by using parts, but it doesn't seem to work. Anytime you have a product and neither of those first two choices work, we start to think, okay, what is something similar to this problem that I could solve? Now, if this question were t cubed e to the t, tabular method or regular parts all day long. The problem here is that this t squared is messing things up. As long as that power is squared, it's not a linear thing, I can't really do parts with this or even the tabular method. So that's my hint. If I want to do parts or if I want to use the tabular method on this problem, then I need to convert it to maybe e to the u. And we do that with u substitution. So if u is, let's use a different variable so I can use u and dv for parts. Let p equal to t squared. Then dp dt is equal to 2t. Or dp is equal to 2t dt. So this is just the derivative. This is moving the dt over to the other side. And now I can start thinking, I have e to the t squared. So this I can replace with e to the p. I have a 2t, but 2 is cheap. I don't have to worry about the 2. I have a t dt here, but what I need to replace is t cubed. So let me pause and think. Okay, so let me do this. I'm going to rewrite this problem as, I'm going to leave a little space, e to the t squared. And because I can only deal with one of these t's, let me write that here, t dt. But I had t cubed, so how many t's are left over, unaccounted for? I had t cubed, I yanked one of those t's out, and I placed it right here. So we should have two of those t's left, t squared, because t squared times t gives us t cubed. But lo and behold, wasn't t squared p? So this is maybe, you can call it a double substitution. It's just substitution. And because I have a t dt and not a 2t dt, I can divide the 2 out and say dp over 2 is equal to t times dt. That's what I really want. So now when I do the substitution, when I go to p land, I'm going to rewrite this integral as p, because this is going to get replaced with p. This is going to get replaced with e to the p times this is going to get replaced with dp over 2. Okay, well, over 2 is a constant, so I don't have to keep it inside. I can yank it outside. I don't want to see it. It makes it annoying. P times e to the p dp. But this is a perfect candidate for the tabular method because now this looks like x to the linear, or x to the n times an exponential function raised to a linear. P is just a single power. It's not p squared, it's not p cubed. So here you can either use just regular UDV parts, or you can use the tabular method. So I'll stop here, let you finish. You should be able to take it from here. Setting up these problems is somewhat spicy, but once you get to here, tabular method should take over, or just regular parts should take over.